Hey everyone, in this video we're looking at the section in your science resource guide on lasers, but the beginning of this section talks about kind of the wave particle duality, the quantum model of the atom, and we have to understand electron transitions before you can understand really the parts of the lasers. You covered some of this if you've had pre-AP chemistry. This would have been like Unit 4 around October. So think back and look in your notebooks if you are a former chemistry student to see how much of this you have. But let's just go through it. A lot of theoretical stuff, and then I will attach separately some photoelectric effect models for you to look at. Well, let's begin this with the quantum concept. Prior to 1900, physicists and other scientists always viewed light as this continuous stream of Newton started this in the 1600s, and he called them like little corpuscles of light that was continuous. It always formed a rainbow. But people started observing things that didn't correspond to that idea. Max Planck noticed that when things glowed hot, that they didn't just go from like glowing orange and then kind of a darker orange to then maybe a really, really dark orange. No, the colors jumped from like red to orange to yellow, and there was really not much in between. So that was unusual, because if light was just this continuous stream, you should have seen different shades of orange all the time. So Planck came up with this idea that instead of energy such as light or infrared, thermal energy, being continuously released, that it was released instead in these very specific integral amounts. And he called those quanta, and that word is what has led us into quantum theory. So at the time Planck did this, he still thought of light as being like a wave. The particle part doesn't come quite yet. So he's still working out the kinks on this. Now, if you look at the equation at the bottom of the page, this is the equation you used in pre-AP chemistry, and I addressed this in one of the earlier videos. But this E equals HF is the energy required to find a photon. And that's the way we worked it in pre-AP chemistry. Now, as we're moving on here, let me add a little something extra to that equation. It can also be used as delta E equals HF. And that's going to be important moving forward. I'm not going to do any math with it right now, but when we get to the appropriate slide, I'm going to refer you back to using this equation with the delta E in front of it. Remember, delta means change in. So the H in this, Planck's constant, is the fundamental unit or the fundamental amount of energy in nature. That's like the packet. And so when you start calculating quantums, there's always some multiple factor. In fact, your resource guide, the equation is E equals NHF, where N is the factor. There's always some factor of this fundamental quantity, H times F. Now, the idea of light being a wave starts taking a hit thanks to Einstein and the photoelectric effect. Again, I'm going to attach some information, a separate activity with photoelectric effect. But in 1905, Einstein published a paper on the photoelectric effect. And here's the main idea. It proved that energy can act like a particle, that light can act like a particle as well as a wave. So what he did was he looked at, and on this sheet of metal right here, what's illustrated are the electrons, and these would be called surface electrons. This could be any thickness of metal, but we all know that electrons are right on the surface of a metal. And what's being illustrated here is incoming light, and light has energy. And so if that light's going to deliver energy, and if it delivers the right amount of energy, it'll kick the electron off the surface of the metal, and then that can be seen as an electric current of some sort. This technology's been around. Supermarket doors opening as you approach, things like that. And so Einstein looked at this incoming beam, and he wanted to experiment, like what would do it, what wouldn't do it. So he noticed for a piece of metal that like red light was very weak. It didn't happen a lot. Yellow was better, but not perfect. But as you got up toward the blues and the violets of the Roy G. Biv spectrum, that this effect happened more commonly. So he knew that these colors were more energetic. And they were what's happening is they're delivering more energy. He called these little bundles of energy that were being delivered photons. And the photon can be defined as a particle of radiation with no mass that carries one of those quantums of energy that I showed you. Okay, and we could also, again, write this equation as delta E of the photon. All right, so the photoelectric effect was important because it introduced the idea of photons, these particles of energy, these particles of light. And now we get into the Bohr model of the atom. This is important because in the early 1900s, we discovered kind of what the atom was not a solid sphere. We talked about in class when you had chemistry, the Thomson model, the plum pudding. And then Rutherford discovers the nucleus. It comes up with the nuclear model of the atom. And from that point forward, everyone was concerned with understanding what the electrons in the electron cloud looked like. And Bohr was the first, let's back it up. Rutherford said that the electrons were just out there, outside the nucleus, and they were sort of orbiting randomly like planets would orbit a solar system, in a solar system. But Bohr said that's not exactly right. Through his thinking and hypotheses, he deduced that the electrons are actually on fixed rings. They can't just be anywhere. They had to be at fixed distances to the nucleus. Of course, those distances would change from atom to atom because the number of protons in the nucleus and the other electrons interfering would change things a bit, but for the most part, every element had a fixed set, a fixed distance, a fixed diameter for these rings that the electrons could be on.
Is there no UIL practice?
No, remember I canceled it because everybody's getting caught up on work today, since we were gone all day Saturday.
Oh, okay.
We're going to be back Thursday. All right, just don't mind that interruption. All right, so back to this this Bohr model thing here. So we have these rings, and the lowest ring, the one closest to the nucleus, is the ground state. Well, that's for hydrogen, because hydrogen only has the one electron, so it wants to be as close to the nucleus as it can be. So that would be the ground state for hydrogen. But when electrons are in the lowest available energy levels, and if you remember from chemistry, orbitals and things like that, you don't need orbitals for this ACDEC stuff, but just remember it from chemistry. When electrons are in the lowest available place, then that's what's called the ground state, and that's where they're always trying to get. We can excite electrons, and this is a very, very important part of this for understanding the ACDEC. Electrons can be excited. We can energize them. We can energize them in a couple of ways. We can heat them. We can run electricity through them. We can do other things. And when electrons are excited, they're absorbing energy, and they jump up, to these higher energy levels. That relates back to the photoelectric effect, because what was happening there was that the electrons in the surface of the metal were gaining energy, but they were jumping up to energy levels, but they didn't absorb enough to go far out, a high multiple of energy, then they just got stuck. But if they absorbed a lot, then they were able to even go so far from the nucleus that they were being kicked out entirely. So what we're going to show you here in some pictures is that when they fall back, they emit energy. And so that gives us another way to calculate the energy of a photon. Instead of HF, we can do the change in energy is going to be level 2 minus level 1, for example. So that would be the energy associated with level 1 minus the energy associated with level 2. All right, so one little throw in here. I'm only throwing this slide in because it was mentioned in the resource guide, the Pauli exclusion principle. It was mentioned specifically on page let's see, 44. And it says the Pauli exclusion principle, and it has to do with the Bohr model and these emission spectra. So remember from chemistry, we talked about this in chemistry, no two electrons can have the same set of 4 quantum numbers. When we did our orbital notations in chemistry, those of you who've had chemistry, I realize some of you have not, we filled electrons into orbital diagrams. There was an up arrow and a down arrow. And Pauli's exclusion principle is the one that told us we had to have an up and a down. And since there's only 2 possible states for that, an up and a down, then that's what limits us to how many electrons that we can put into an orbital. So what I'll do is I'll post my my old video from the chemistry class talking about quantum numbers and quantum mechanics. You may not have time to go through all that, and it may not be worth your effort. I don't know, but reading this ACDEC guide, sometimes they just throw things in there that don't necessarily have to be there. But as a question writer, I can see stuff like that and recognize that it could possibly be a question. So I'll include that, and I'll leave that up to you. All right, now let's get into the atomic spectra here. A lot of this next part of the section, starting on 45, has to do with different types of spectra. So when we talk about sunlight or light coming out of flashlight or light bulbs, that is called white light because it is a continuous spectrum. All the colors, all the shades, all the wavelengths of light come off at once. Now we notice that when elements are heated until glowing, though, they only give off wavelengths, certain wavelengths. I'll show you a picture here in the next slide or two. So we don't get a continuous spectrum when we look at elements. Like think back in chemistry class again, if you had it, where we had those bulbs and we looked at those crazy glasses and we saw those vertical lines. Those lines correspond to jumps between energy levels by the electrons. All right, so here's what I'm talking about. In this top one, we have a continuous spectrum. That's when you get all colors, all shades, all wavelengths of light blending smoothly together. All right, the one in the middle is called an emission spectra. This is what we looked at in chemistry class and what I was referring to. So we don't get the continuous every wavelength. Some atoms only have the ability to give off specific wavelengths because their energy levels are set. And when an electron travels from energy level 3 to 2, for example, that difference in energy corresponds to only one piece of the continuous spectrum, and that's what we see as a single bar or a single wavelength of light. So that's an emission spectra when it glows and gives off that light. The opposite of an emission spectra is the absorption spectra. So what would happen here is if you have, for example, a gas cloud in outer space, like a gas cloud of, say, I don't know, helium gas. And if you shine light into that cloud, like from a flashlight or from a star, white light coming through that cloud, then the atoms of neon are going to interact with that light. And the electrons in the helium, the atoms of helium have electrons, and those electrons are going to absorb certain frequencies of the light that's being passed through it. And so the light that comes out is going to have gaps like you see here in this absorption spectra. And those gaps correlate to the transitions, the electron transitions between energy levels as those electrons inside the helium atom absorb the energy of the incoming light. So they jump up and that leaves gaps. Emission spectra, on the other hand, are when electrons fall down back to a ground state and they give off that light, and that's the difference. You can see here for this specific element, I think this is I think this is hydrogen. I think it is. So you can see this is the spectrum from hydrogen. So if I have a hydrogen discharge tube, put some electricity into it, excite the electrons, let them fall back, I get these vertical bars that you see here. And then for the absorption spectra, if I had a cloud of hydrogen gas, shine light through it, and then I'm going to see these bars missing on the light that comes out as those energies are absorbed. So there is the spectrum tube. Maybe that rings a bell if you've seen that before in class or any of your classes. And we get very specific wavelengths of light for hydrogen. This is just a quick how it works. You know, we energize the gas. It starts, so the electrons get energized. They fall down. All that's taking place inside the bulb. The light is emitted as the electrons transition. We pass it through a slit to polarize it, and then we pass that light through a prism. And the prism, due to the laws of refraction we covered in a different video, light bends at different angles as it goes through, white light that is, and it separates into its components. And those components come out and end up being the vertical bars we saw. Now here's the meat of it right here. This is the Bohr model. And we can see here, this is hydrogen. So we have the single electron here for hydrogen. And this squiggly line here represents the incoming energy, a photon of whatever it is. It could be visible light, it could be an X-ray, it could be infrared, it could be whatever. It's going to interact with the electron, and currently this electron is in the ground state, the lowest possible energy level. It's going to absorb it, and it jumps up. Okay, if it absorbs the right amount, it'll jump up to 2. If it absorbs double that, it'll jump up to 3, you know, whatever factor it is. And then on this picture over here, we see the opposite. If an electron is in what we call an excited state, and it falls back down toward the ground state, as you see in upcoming slides and in your reading, it doesn't have to fall all the way to the ground state. It could stop along the way, like a train at different stations along the way. And so that energy that had to be excited has to be given off. And that's how we get emission spectra. So I'm not going to go too much into this one. I didn't see a lot of this in the resource guide, but we have talked about this before in your class. These are the different types of emission spectra. I'll just say briefly that for visible light, to make these visible spectra like you see down here, that is when electrons land on the second energy level. So they don't fall back necessarily to the ground state for hydrogen. The electron would land on energy level 2 instead of 1. If it fell all the way back to the first energy level, the amount of energy given off there is actually pretty large. It's in the UV range, so you couldn't actually see that unless you had UV glasses on. So let's just move on past that. This diagram, I think, is more beneficial to help you understand what's going on. It one more time takes the hydrogen spectra, and we can see these different bands of light, and we can see that for the color red, it corresponds to a transition from n equals 2, the third energy level, to the second energy level. And it's very specifically this wavelength, therefore this frequency of red light. And if you go from 4 to 2, then that's going to give you a little bit longer wavelength of light. Let's trace this arrow, and that's going to be green. If I start from 5, let's trace this arrow. That's the transition that gives me this bluish color, whatever you want to call it, indigo. And then finally, if you know, from 6 to 2, that'll give me the blue one. Okay. Now, if it falls on energy level 1, all these energy transitions here are vast. And so all of these transitions in N01 are down here into the ultraviolet, beyond violet. And you can see the different types. But this is a key concept as you look at the idea of the Bohr model. All right, now moving into some applications of this. These are some more vocabulary words that you have from your resource guide. It talks about incandescence. So incandescence is glowing. It's the exciting of these electrons and atoms due to heat or thermal energy being added. So we're jumping these electrons up to higher energy levels. If we did this to a gas, we would get very discrete wavelengths. So we would get a specific color of light. Okay, so very similar to those emission spectra. But if we do it for solids, solids are going to give us a more continuous spectrum. And the resource guide tells us that's because in solids, the atoms are more closely packed. There's actually some overlap in their electrons, clouds. There's some interference from one atom to the other. So they affect each other. So with all those different possibilities added into the mix, for solids, we get a continuous spectrum when things glow, get so hot they glow or they incandesce. And then we have an interesting an interesting little thing here. We have a relationship between the wavelength, the peak wavelength we see when something's, for example, glowing hot, and the temperature it's at. So as the temperature goes up, this temperature, the value of the wavelength is going to decrease. That's what inverse means. Now think about what that means in terms of the EMR spectrum. As the wavelength decreases, that is going to be your higher energy colors and your higher energy EMRs. So if I jump from 500 Kelvin to say 800 Kelvin, then my wavelength is going to decrease. So that may mean that I'm jumping up to a peak from, let's say, red to violet, for example. Okay, so things get hotter, they start glowing at brighter colors closer toward blue and then closer toward violet if you keep on into the ultraviolet and then X-ray. This graph is one similar to the one in your resource guide, except of course I found one that's in color. So you can probably expect to see one of these on the science test. And all it's showing is that peak wavelength. So for example, at 3000 Kelvin, this bottom one, that's a fairly low temperature for this substance, I guess. And so the wavelength that you see would be in the infrared. It would just be hot. You couldn't see it. But if you put some infrared glasses on, some night vision goggles or something like that, then maybe you would see some glowing from it, which otherwise you wouldn't be able to see it. But as we increase the temperature, you see this peak keeps going further and further to the left until that wavelength drops, and that wavelength is getting shorter and shorter, so the peaks are getting closer together until eventually you will start seeing this substance at 5000 Kelvin jump into the glowing red hot range. And if we keep increasing the temperature, you see the peaks shift some more, squarely in the visible range, and then you'll start seeing it glow yellow hot. If we kept doing this, maybe say 8000 Kelvin, this peak would shift more, and it would actually put us into the violet glowing blue hot, or at that point it would actually be probably white hot. But that's the way it works. So incandescent is glowing because you're hot and you're excited. All the electrons are excited and they're doing all their transitions up and down. So fluorescence is similar. We excite the electrons in some way. It could be as simple as shining a light on it. But as soon as you remove the source, everything jumps back to normal. The electrons immediately go back and the whole process stops. This is the phenomenon you see with black lights. You've all experienced black lights. You know when you shine a black light on something, it has this nice bright color, and as soon as you take the black light away from it, it just goes back out. It doesn't sit there and glow afterwards. So that's fluorescence. We use it in to be able to check money. You've probably been to Walmart or the grocery store, and you've seen the cashier look at a big bill with this little tiny, like a little pin flashlight looking thing. That's a UV light, and what they're doing is they're shining that UV light at the money to see if it fluoresces like it's supposed to be. Some counterfeiters, especially cheap ones, don't have the ability to add the fluorescent materials to the money they're counterfeiting. So they're looking for that glow. As soon as they turn it off, the money quits glowing. So that, again, when it glows under energizing, but goes immediately back to normal, that is fluorescing. Phosphorescence is the same idea, except it takes a little time for the glowing to stop. This is the phenomenon behind glow sticks and behind the glow-in-the-dark stars. It's a metastable state. We excite those electrons and they go up to these excited states, but for some materials, those excited states are kind of okay. For most materials, they're terrible, and it transitions back in nanoseconds or microseconds. But for these phosphorescent materials, the excited state is metastable, and it takes maybe minutes or hours and sometimes days for the glow to go away. And if you look in this bottom picture here, you'll see we have, I think it's a radioactive material like uranium salts, and you're exciting it. So maybe you're shining a UV light or just a really bright light, or maybe it's just even sunlight, and the electrons are becoming excited in this material. So we shut the light off, and then you can see that it's still glowing. And time is passing. In this case, it's a very short amount of time, but the glow gradually decreases. That is phosphorescence. This also happens in nature with bioluminescence. Most of that is phosphorescence. And yes, phosphorus is an atom, a substance that does this. All right, well, that takes us up to the part we need to start talking about lasers. I'll do a final video on lasers, but look at the rest of the attachments on this particular assignment and catch yourself up on photoelectric effect and quantum theory if you want to. Come by D222 if you have any questions about this material.